I am a PhD student in the Department of Mathematics at the Open University in UK. So my research is about dynamical systems, right? We try to understand what's the, so we have a set of points in some space and some evolution rule that tells us how the points change with time. And we try to understand what are the limit behaviors of these things. Dynamical systems can be classified into two big types, continuous ones, when the set of times are the real numbers, and this evolution rule is given by an ordinary differential equation, or the discrete ones, when the times is just the integers, and then the evolution is given by the iteration of a certain map. Right. Well, just a warning. Of course, when you deal with evolution, you never know what's going to happen, so it's good to take care. So, more precisely, my research deals with, my area is called complex dynamics, which means that among the two types before, I do the discrete version, so I iterate functions, and my functions are analytic functions on the complex plane. So I work with complex numbers. I start with a seed, say, does this work? Well, z0, and then you apply the function, and you get a new point, z1. Then you compute the image again of this point, you get z2. And you take this process, so for every initial condition, you get a sequence of iterates. And you want to understand what's the behavior of this orbit, right? So this is the typical phase space that we have. This is the iteration of a polynomial map. You have the polynomial written down. So what's this? The colors describe what happens with the orbit. All the black points have bounded orbit. And in particular, they get attracted to a 3-periodic orbit that, if I could point, like the initial point is in the big component, then goes to the right, to the left, and comes down again. So all the black points eventually go close to this 3-periodic orbit. All the other points, they escape to infinity. So when you iterate them, every time the modulus of the images are larger and larger. This is a typical behavior of a polynomial, because if you have a point with very big modulus, the complex modulus, then the image by the polynomial essentially will behave as z to the d, so you will get bigger and bigger. So the interesting part happens in a very small part of the phase space. In between these two behaviors, the escaping points and the ones with bounded orbit, you have all this beautiful fractal set that is the set of chaotic points, right? So they have dense periodic orbits, they have sensitive dependence on initial conditions, etc. All the features of deterministic chaos, right? But we don't study polynomials in my research group. We do transcendental dynamics, which means that things are a little bit more difficult. What does it mean, transcendental? Transcendental means that the function has some essential singularity. This is the precise definition of what is an essential singularity, but you should really understand it as just a bad point, right? And why it's a bad point? So this is the theorem that tells us that studying transcendental functions is much more difficult. What does it say? When you have an essential singularity and your point falls in a neighborhood of this bad point, then the image, instead of converging to like infinity, the image can be essentially any point of the complex plane with at most one exception, right? This is the picture of what is an essential singularity. So the point at infinity for the exponential is an essential singularity. This is exponential of 1 over z, which means that 0 is this singularity. And you can see that if you approach from the right, well, the colors here means the modulus and the argument of f of z, right? F is exponential of 1 over z. If you approach from the right, you tend to plus infinity. If you approach from the left, you tend to 0. But in any other direction, you can see that there are infinitely many different colors, which means that the limit doesn't exist. So this is, we have to deal with these guys, the essential singularities. And essentially, the kind of functions that you can study follow in these three big classes. The first one, when you don't have any essential singularity. For instance, this is the case of polynomials, the one that I showed you before. The second case, when you have one essential singularity. So this is the case for entire functions, like functions that are analytic in all the complex plane, except at infinity. Or the third big class is the ones that are analytic. Is that the time? Huh? Is that the clock? Oh. Well, I just wanted to say that my research focuses in this third class here, and thank you very much for your attention.
Thank you.